Hi, I'm Thuy, but you guys can call me Shun. I will talk about setter stable and fractionally log-concave polynomial and the application in counting matching in planar graph. This is a joint work with Yegane, Nima, Kiran, and we are all at Stanford. So first, let's define the monomer distribution. The goal is to sample from this distribution. So let G be a graph. The monomer dimer distribution is a distribution over subsets of H sub G supported on the margins of G. A margin, if you don't remember, is a spanning subgraph of G where every vertex has degree as small 1. So this distribution had been studied in physics in the 70s. We will consider a variant called the monomer distribution. This is a distribution over a subset of the set vertices V, where mu of S is the sum of phi of M for M being a perfect matching on the complement of S in V. So let's see an example. So in this picture, mu of the set D and E is 2 because there is 2 matching on the complement of this set, whereas mu of the set consists of A and F is 1 because there are only 1 matching on the complement of the set A and F. So now we consider the problem of counting matching in graph. A K matching is a matching that consists of exactly K edges. And the perfect matching is the matching that consists exactly V number of V divided by 2. So the problem of exactly counting perfect matching even on bipartite graph is equivalent to the problem of computing the permanent. So this is sharply complete. This is solved by Valiant in the 1987. But on planar graph, exactly counting perfect matching is in P. On the other hand, for K matching, even counting K matching in exactly counting K matching in planar graph is sharply complete, and this is solved by Jerome also in 1987. And in general, counting bipartite, counting perfect matching exactly in bipartite or in general graph is also sharply complete. So in general, we can reduce counting K matching to counting perfect matching. If we want to count K matching on a graph G, we can create G prime by adding n minus 2K dummy nodes that is connected to every node in G. Then counting perfect matching in G prime is equivalent to counting K matching in G. The reduction from perfect matching to K matching is easy. You just need to include singleton vertices. So if G is bipartite, then this K matching to perfect matching reduction can be modified to make G prime also bipartite. But for G being planar, this reduction doesn't work. And in general, there cannot be a reduction from counting K matching to counting perfect matching on planar graph because of the result in the previous table that exact counting K matching in planar graph is sharply complete, but exact counting perfect matching in planar graph is in P. So Jerome asked whether we can count K matching on planar graph approximately. So here's a table that summarizes previous results about approximate counting matching. By approximate counting, I mean to get a 1 plus epsilon approximation with a runtime that is polynomially dependent on 1 over epsilon. And in this work, we will show that counting K matching in planar graph is approximately is in P. Now for so in general, there's a equivalent between counting and sampling by Jerome, Valiant, and Bajrani. And so instead of consider the problem of counting planar, counting k-matching in planar graph, we consider the problem of like sampling from the monomer distribution that I described earlier. So, okay, so for distribution mu, we let its generating polynomial be defined follow. And so for any external field, which is a vector in Rn, the scale distribution lambda scale by mu scale by lambda is generated by f mu, like where the variable are scaled by lambda I. And our question will be like, what property of the generating polynomial imply efficient sampling algorithm for mu? So we introduce the notion of setter stability. A multivariate polynomial f is setter stable if it has no root in the S alpha setter on the complex length. And we say that mu is alpha setter stable if f mu is. This is a generalization of well-studied notion like real stability or Hurwitz stability. The nice thing about setter stability is that it degrades smoothly under certain operation, like truncation or equivalently intersecting the cardinality constraint. So just remember for this talk, alpha is a constant between 0 and 1. Mostly alpha will be like either 1/2 or 1, and the bigger alpha is, the better. So let's see some example. The monomer distribution that I defined earlier is one setter stable, or in the literature, it's also known as Hurwitz stable. This is proved by Hellman and Leaf in 1972. The determinantal point process distribution with kernel L that is non-symmetric positive semi-definite is one setter stable. And in general, if mu is one setter stable, then the truncated distribution mu k, which is mu intersecting the cardinality constraint, so mu restricted or set upside, that is k. This is 1/2 setter stable. So with that, we have the truncated monomer distribution, mu k, or the truncated DPP distribution with non-symmetric positive semi-definite kernel on 1/2 setter stable. So here's the outline of our technique. So we will show that setter stable imply bounded row norm of a correlation matrix. This was defined in prior work by Anari, Liu, and Ovaisgaran in last year in Fox. This in turn implies fractional log-concavity, which is a stronger form of spectral independence. Then using some modification of the framework by Anari, Liu, Ovaisgaran, and I left below, we get fast mixing of a multi-step down of random walk to sample from mu. So here's the general recipe to sample from distribution on discrete subset. We have seen a lot of recent success. So we view distribution as the weighted hypergraph, or simply show complex. Where the vertex are the element of the growth set. So for example, the vertex are integer from 1 to n in all of our examples. and the hyper H as subset in the support of mu with the weight given by mu. We enforce that the subset of hyper H is also a hyper H, so the hypergraph is somewhat like downward closed. And this structure is called a simplicial complex. We saw that this simplicial complex is a high-dimensional expander, and then this implies that the random walk on this simplicial complex mixes fast. So let's define this random walk. So here the top level are subset of size 3 drawn from a set of 6 vectors, and the bottom level are subset of size 2. Top and bottom form a bipartite graph. There's an H between S in the top and T in the bottom, if and only if T is contained in S. The random walk starts at set S in the top. It drops an element uniformly at random to move to a set in the lower level. Then it adds one element with probability proportional to the mu of the resulting subset to move back up. So this is the one-step down-up walk. We can also define a multi-step version. So instead of dropping one element, you drop L element uniformly at random. So here L equal to 2. Then again, you add L element to move back up with probability proportional to the resulting subset. So now we want to sample from mu k using down-up walk. Mu k is the truncated monomer distribution, but the k to k minus 1 down-up walk or the one-step down-up walk doesn't mix. So in this example, say originally we are at the set S that consists of the node A and B. Now we drop one element, say we get B, but now we cannot add an element except for A because mu k B C or mu k B D are all 0. But the walk from k to k minus 4, which is the 4-step down-up walk does. So here's an illustration of how the 4-step down-up walk looks like. So our main technical contribution is to show that sector stability implies bounded correlation, or like bounded row norm of the correlation matrix. So let's define this correlation matrix. Think of it as the covariant matrix where the ith row is scaled by 1 over pi. Pi is the marginal of I with respect to mu. It is related to the transition matrix of the walk between singleton and pair in the high-dimensional simplicial complex. So here's our main theorem. Sector stability implies bounded correlation of all scale distribution of mu with arbitrary scaling. Of course, that includes the scale of like on 1, which is just mu itself. And this bounded correlation matrix with respect to all scaling is exactly our definition of fractionally log-concave. So here's the definition. And the theorem in the previous slide showed that alpha sector stable implies alpha over 2 fractional log-concavity. Now, so for the scale distribution with lambda I set to infinity, this distribution is equivalent to the distribution mu condition on the ith element being included. So fractionally log-concave implies spectral boundedness of mu and all its conditional distribution, which is the same as spectral independence. So here, alpha fractionally log-concave implies one over alpha spectral independence. So then from that point on, we got the fast sampling result using existing framework. And in general, we can prove that if F is root-free in a region containing the positive real axis, then we also have spectral independence. So our technique is a little bit more general than just for Setter stable. Thank you for listening.